So I'd like to take this, this night to explain to you something we've been working on at Neo4j, especially in my group. This new technology that we've implemented, we're calling it Causal Clustering. And it's a new way to cluster your database to give you much better service and run much higher production apps. So I'd like to explain all that. So I'll start by explaining maybe what Neo4j is. So you have a world of data, all these data points that are connected. Somehow there's all these disparate data. This is sort of the graph, the idea. And this is kind of what Neo4j is. Neo4j is this kind of graph idea, but put into one small box, so your server. So this is, Neo4j is your graph in a box. And clustering is basically taking yet one Neo4j box and expanding out to many, many instances of that, taking that graph on many machines, so many boxes. And why would you want to do things like clustering? Well, there are three main themes and main reasons why you do it. The first one is higher throughput. So when you have more machines, you can have higher throughput because you can spread the load across all these different servers. The second reason is for data redundancy. So what does that mean? Well, let's say you have that one box and something bad happens, the data is gone, and so you've lost everything. And you want to have many more machines, so that way if something does happen bad again, well, you still have lost that one, but you've got extra ones there that are perfectly fine. So data redundancy is a big one. And the third one is high availability. So what happens when one of your machines crashes? Well, the data might be gone, or maybe it's not crashed, but it's just offline. So your website or whatever service you're running doesn't work anymore. But if you have many machines, if you are routing to that one and it breaks, you can just reroute, and the service you're running will continue just fine. So these are three main reasons why you'd want to cluster your application. And with the new Neo4j 3.1, with causal clustering, you've got all that plus more. You've got massive throughput, but now with 3.1, you can run it with bigger clusters for even bigger throughput. We already had data redundancy, but now with 3.1, you've got consensus commit, so you have even better data consistency and data guarantees. And we've also had high availability, but now you've got more features to make it much easier to write applications. So you have built-in load balancing, for example, to get the load spread across all those machines we're running on. So these are all new features that make 3.1 a really awesome release of Neo4j. So I'll talk about it more specifically how this new architecture works, called causal clustering. So there are two main parts of the cluster. These are roles for the servers in the cluster to take. So one of them is called the core group. So these are machines that take part in one function that we call the core. And then you have many more machines that are part of the read replica group that take part in a different function of the clusters. And I'll explain exactly what they do going on. But the important thing to note at this stage is that you have the core and the read replicas. And this core set is a smaller number of machines than these read replicas. So when you deploy your application cluster, you'd have machines that are either put in one of these two groups. So the most important one is probably the core. And what it is, like I said, a small group of Neo4j databases. They do a fault-tolerant consensus commit protocol. So that means they get consensus before they commit the data. And they're responsibility for data safety. So in the event of something bad happening, you've got this core group that will take care of that the data is safe. And so how does it look when you interact with this core group? Well, you're interacting with it with the Neo4j driver. We have now official drivers for many languages. So there's a Neo4j driver that you'll use. And you'll have this interaction with the core group where you'll send a request that the driver knows a machine that it can send it to. That first machine will acknowledge that, it will receive it and save that data that you've tried to commit to the database. It will then replicate it to many other machines. Once a quorum of machines have saved it on their internal, on their servers, there may be some other machines that are still maybe getting the data or processing it somehow. But those machines that have received it will respond back to the initial first machine that received the request. And because it has a quorum, so a majority of machines have saved it, it's then safe to respond back to the driver or the end application to you and tell you that the data has been saved safely. and sometime later, asynchronously, the rest of the machines in the cluster will become up to date and have that data as well. And so you can have data safety as long as at least half the machines have saved it. And that's a property of clustering and things like that. So if there's a partition and anything like that, you will never get a state where it's inconsistent because you have a majority have acknowledged that this is the state of the database. And so how does this all work? Well, we do everything with Raft. So Raft is a clustering algorithm. You may have heard of Paxos as another kind of algorithm, but Raft is a newer one from a few years ago that was written about. And the important part about it is that so it's new research, but the main goal of it, in comparison to Paxos, is that this new Raft research is designed to be easy to understand. So where Paxos is correct, it's difficult to understand and implement. Raft is also correct, but it's much easier to understand and much easier to implement. When it's easier to implement, that means there's less bugs. It's easier to focus on things like performance, for example. So we've used Raft to get this consensus commit protocol. And how that works is essentially how I explained it. You have many machines that are sending messages throughout the cluster for internal state things to get consensus on getting a consistent transaction log across all the machines. So you don't really need to understand any of that, but it's an internal algorithm that's sending all these messages to all the machines to get a safe transaction log of all your attempted writes to the database. And so how does that work with Neo4j? So we have our own implementation of Raft, and in Raft land, you might have attempted writes to the database that aren't committed or they fail somehow. So maybe you write to a machine and that machine then dies. It wasn't committed, so you don't lose any data. But there are times where the Raft log on all the machines might be inconsistent. So they're consistent up to a certain point, but the very end of the logs might have different data because you're still replicating it around. But then in your Neo4j application on the Neo4j servers, you do have a consistent log. So all these machines are consistent. They might be replicating to each other still, so it might not be complete, but there will be they'll have the same log. And like I said, actually, in Raft lands, you might have transactions that are like removed from the log, so they were attempted to be committed, but they were rolled back, or things like that, or so it didn't get consensus on it. So they might exist at some point in the log, but that's not anything you have to worry about because it's something that's hidden underneath this layer of Neo4j. But that's just kind of how it works internally. So I won't dwell on that too much, but that's basically how the core works. It's this machines that do Raft, send messages around, try to get consensus on them, and then when they do, it then responds back to you at the higher level that everything's been saved safely. So the other big part of this puzzle is read replicas. They are completely different in that they don't take part in this consensus commit protocol, but they are for nothing but speed. So they're just for massively scaling out your read capabilities. So they're read-only, so you don't write to them, and they're kind of disposable in a way. So you don't have to worry about them dying or being shut down or anything. So they're perfect for auto-scaling application for read capacity. So you can just spin them up, and they'll be there, and then you can tear them down whenever you don't need them anymore. So they work much simpler. So you'll write something to the database. The core cluster will get that, and then those core cluster members will then propagate it down to all the read machines. And so when you do those reads, you can do those reads against these read replicas, and they will give you whatever your query was. But the point is that it won't be going against the core always, and that saves them capacity to do more writes. So you can get your overall application much faster. And so why do we choose this architecture? Well, it's based on how you actually use Neo4j and how you use graph databases. So typically when you're writing something to the graph database, you're writing a small point of information about a certain node or relationship. And so when you look at the whole graph, it's a small interaction that you're just touching something, changing some values, adding something, and then you're done. But when you're doing reads on the graph, they're much more intensive operations because you're maybe wanting to find connections between things and finding patterns, and that ends up connecting more nodes in the graph, and that takes up more capacity for the database to do all those reads. And so you have a much larger part of the graph is touched on these reads. And so for writes, you don't need, you need to be fast for writes, but you don't need to touch much of the graph. So we can scale out this read part by having these read replicas that you can then do these large queries on. So you can have certain, you can even have read replicas that are just for certain massive queries that you run occasionally. And then that saves the core group from having to do all this work, and then they can focus on just doing the small writes. And so that's the core, and that's read replicas. That's the architecture, the topology of how this new causal clustering works, and why we think it's a really great way to design this clustering for Neo4j. So I want to just talk about consistency. So this is an important part of causal clustering, but clustering in general, because there are many things that can go wrong if you don't have consistent writes to your database. So you can have a state of the cluster where certain machines are more or less up to date compared to their other peers. And so you might have this state where maybe this machine at the top has transaction 11, but the other machines might not have had that replicated yet. And so you can see that that would be replicated in a graph with the same number of nodes, but they're missing maybe the node that's in transaction 11. And so how does that affect you if you're writing an application? Well, say you're writing an app that's like a web store. So you have this sort of login step at the very end. And so you make your user log in, so that's to create an account. They create that account, so then they have to log in again with those credentials they just created. So they go and they log in. And when they try to log in, they get this kind of error, like, oh, the account's not found. But that's really unusual because, well, of course, we just saw the user created the account. So if they wait a second, or wait a few seconds and hit the login button again, well, it'll probably work. And this is an example for logging in or something, but maybe you've seen it for other situations, like if you're updating your profile picture or something like that, you'll change something and then you'll have to go back to the home page and you won't see your change until you refresh a couple times. So it takes us a second to update. And why is that happening? Well, the answer is that this is an eventually consistent system that you're interacting with. So it's a system where the consistency will take some time to propagate to the other machines. It's for you to see the update because you're doing an interaction with one machine, an update, and then you're trying to read it from another machine, and the other machine doesn't have that yet. So that's why you sometimes get data that's old. And so what's going on in the cluster on the on the backend side is that you do the account creation that goes to one machine. You'll add that user, so that gets added to the graph or the database, whatever you're using. It might get replicated somewhere else, then it returns. And then when the user tries to log in again, that login attempt, well, the graph, that data gets propagated still around. But by the time you log in, you've tried to go to this server, perhaps, it can happen. But that one doesn't have that data yet. So when you try to read it, well, it's not going to work because you just ended up routed to whatever server you happen to be on. And this can happen. This isn't just a Neo4j thing. This is for a lot of systems. This is basically any system that's not causally consistent. And so how we can fix this is a major feature of new causal clustering in Neo4j is this idea of a bookmark. So it's similar to like a session token, and it's opaque, so you can port it around to whatever application you're using. And it's a representation of the most recent state of the graph from the user's last interaction with it. And you can use that to ensure that the user doesn't have an interaction with the database that is any less recent than that. And so if we see this example again with the bookmark, so you create that account, you write to the server, it replicates it, and it responds back, but you responds back with this bookmark metadata about the results of that transaction. So you're told in the application the transaction was succeeded. Here's a bookmark for you to use. And then your application can keep that bookmark. And when your user interacts with the database again, they can send it again with a request for the login. And when you get routed to a server that's still behind, it will ensure that it won't respond back with stale data. So it will wait, in this case, until it gets the transaction replicated to itself, and then it will respond back to the user. So that way the user doesn't get this having to reload the page kind of experience. So how do you write an application with this causal clustering? Well, you use the Neo4j driver for this. So for things like bookmarking, and that's all taken care of for you in the official drivers. So for whatever language you're going to use, you can use that, and that works with Bolt. So whatever situation you're running with, it's going to be really fast. You don't have to worry about speed loss by using the drivers or anything. And there are, like I said, there are drivers for many languages. These are the official ones, but you can probably find them for more languages. There's a C driver even. You can find out more online, so at our neo4j.com/developer/language-guides. Or you can pay attention for a bit longer, because I'm going to explain as a demo how to do it at the very end. But basically, the way if you wrote an application for Neo4j 3.0, you use this connection scheme to connect to the database. And now all you have to do is change this to a new scheme called Bolt plus routing, and you'll get all these benefits of the routing features of Neo4j 3.1 drivers. Yeah, and the way you connect to it is you only need to pass in the address of one of the machines. So your application does need to know where the cluster is, but doesn't need to know all the details, just needs to know one member of the core cluster group. So it's a little bit helpful. And so when you sort of deploy your application, your users can connect to your application server. Your application servers will be using the drivers, and drivers will handle the routing to the database layer of where to send the writes and the reads to. So if you're doing reads, it'll automatically go to one of the reads replicas or the core set, or if you're doing a write, it'll automatically go to the core sets for you. So if you're going to do a read, and this is Java code, but it's really simple. Where you create a driver, you open a session on the driver. So it's just telling it, you open a session on it, you declare that you're doing a write, and you begin your transaction. You do your cipher code in here. You tell it to run that, and then you evaluate if anything happened wrong, or that you didn't, wasn't good, and you mark it a success, and it's that simple. Again, I'll show you an example of doing all this. The same thing with reads. You just have to change the access mode to read, but otherwise it's the same way to interact with the database. Yeah, so if you're, what was I going to say? Oh yeah, the bookmarks. So this is the example with the bookmarks. And the way that works is also really simple, is that after you do all this writing to the database, you have this session that your database interaction exists in. You ask that session at any time for the last bookmark, and it gives it back to you as a string that you can then do whatever you want with. So I'll show you an example of how I use it in a web application. So that's the step. That's when you tame the bookmark. You use the bookmark. So yeah, this is how causal clustering works. There's the core, it's updating graph and replicas that are doing queries. Maybe you want to do analysis, huge graph analytic queries that take a long time to run, or other kind of reporting steps. So how do you get it? Well, it's actually been released last week, so you guys can try it out. Neo4j since the middle of December. And the Java driver is available today. The other official drivers will be available in a few weeks. And then you can use this causal clustering and try it out in any application you're building out. And you just go to neo4j.com and you'll see big banners for it. So this is the end of the talk part. So if you have any questions, maybe we can save it for the end. So now I'd like to go and give a demo of writing an application. So I'll just... Okay, so I've chosen to make a website that has pictures that lets you vote on those pictures. So if I do that. So it's really simple, but it's nice because it demonstrates how to use this clustering and how to use bookmarks and such. So this is it. This is the website. I've got 2 photos here. We can add some more later if you want. And you can click vote, and it will add another vote to the database. So I will show you, let's see, so how am I running all this? This is, well, the Neo4j is just running on DigitalOcean, so I've got 4 servers spun up here. So I've got 3 core servers and 1 read replica. And if I go to one, yeah, so deploying the clusters is pretty simple. You just have to, I don't know if I'm still logged in.
Yeah, it looks simple.
Yeah, my Wi-Fi is connected.
Sorry, I gotta.
Yeah, so you deploy your servers, or on DigitalOcean you spin up some droplets. You download Neo4j and unzip it, and then you add 3 or 4 configuration lines to it. So you say, like, what are the other members of the cluster, what address or what interface should you be talking on, and what is this going to be, a core or a read replica. So just basic stuff, and you can even automate that with some small scripts to just spin it up for you. And so I connect it to one of the machines, and if you do a sysinfo query, you can then see the state of the cluster. So this tells me that there is a leader. So in Raft terminology, Raft has leaders and followers. So it tells me that who's the leader, who are the followers, and then it tells me who is the read replica, and then it gives me the addresses for connecting all those and helpful links to just open another window to those other machines. So I can see the cluster topology, and then if you've never seen Neo4j before, you also see a bunch of other information about the database, the transactions, the store size, things like that. So that's how it's set up. So the way that the database is done is I've got, say, pictures, and I don't have that, I have votes. So this is the way the graph is basically, my data model is done like this. So you basically have pictures with URIs, and you have votes that are for certain pictures. And so whenever you click vote, it creates a new node, connects it to whatever picture you voted for, and that's it. It's really simple. And so you can see I've done this in a way where I've got 2 pages, one for eventual consistency and one for causal consistency. So if I'm here, if I go to causal consistency, and then my laptop works, because why wouldn't it? Okay, let's try that again. Probably have to just reload it because I connected to this Wi-Fi. But what I'll see is that if I try to do a vote with the causal clustering enabled, which means I use bookmarks. When I get a vote, I will see the vote replicated because the vote will refresh the page and show me the home page again with the bookmark. If I'm using the eventual consistency model, I won't have those bookmarks, and I've purposely set up the cluster so that there's a long replication delay to emphasize that it does take time to replicate to the different machines. So you do a read, and it will take some time to update, and you might not see the update when you go back to the page. So like I said, I'll get some causal consistency. So I'll click vote here for this person, and there you see it updated. So it went to 98, 99. I'll vote again. And Wi-Fi is a bit slow, but you see that when the page refreshed, if you notice there was the refresh icon there, it refreshed, and then you saw the vote here. And the way that's happening is that when I've done the interaction with the database, I've got a bookmark back. And I've been really lazy, and I've just stuck that bookmark here as a query parameter, which is a string that you're not supposed to look at. But if you do look at it, it just happens to be really human readable, where it just says a TX ID. And so it puts it in the query as a query parameter. And then when you load the page, because when you vote, it redirects you to the home page again with that query parameter. Then it loads the home page. The query parameter is then used in the database read. And that ensures that you get the state of the graph as it was when you hit the vote button or after your vote was registered. And so that's why if ever I click vote, I'm never going to get a page back where I don't have my vote shown. So if I switch to eventual consistency and I click vote, it'll be hard to see kind of, but I'll click vote now and probably messed that up. So I click vote. I reload the page, but the vote count didn't go up. So I can click again, that went up, but now it went up by one. So if I click 3, 4, 5 times, it doesn't go up. But if I go back over here and hit refresh, so Control R, now my votes show up. So that's because, like I said, I'm doing a write to one server, I'm doing a read to another server. There's this replication delay, and it takes a while for that to show up. So when you reload the page, you then finally see it. But of course, in the real world, this shouldn't be that slow, but if you're doing a lot of throughput, things happen, it is slow. And demo, it's just slow because I made it super slow. So I'd just like to show how this all works. So this is a Spring application deployed on Heroku. So if the Heroku bit is not really that complicated. If there's a good tutorial about how to deploy Spring apps on Heroku. So basically the process for that is you do Spring init, Spring you install, and then you create some sort of demo application, so this hello world. You can then git commit that, and then do a Heroku create. So Heroku also something you install their tools. That creates all this, Heroku dynos, creates a remote repository for you. You push that, and it goes live. So I won't dwell on Heroku parts, but my Spring application. So I've got a index page, and the interaction with the database. So is here. So you need some credentials to log on for your driver to connect to the database. So these are simple. These are just environment variables I set. You do a connection to the database. So you initiate your driver. So I do this just in the constructor. So you give it your scheme because that's just here. So it's bulk plus routing. The address of the database, so that's the IP address of one of the machines. And then you pass in your authentication token. So there's also a whole load of security features in Neo4j 3.1. In this example, I'm just using simple username password. And so if you're going to do a write to the database, well, how does that work? So that's this bit. This is similar to the presentation. You have a match, so I try to find the picture you voted for, so that's the value here. So you give me some URI of the picture. I can match that I'll return, and I'll create another vote node, and I'll create a relationship from that node to the picture that you voted for. And then mark that as success. I'll grab the bookmark and return that, which I'll show you because it's in the controller. So I've put this all in a service. It's a Neo4j service. And then if you're going to write, or sorry, if you're going to read to the database, you can pass in some bookmark. You can then create your driver in read mode, and you can create a transaction either with the bookmark or without, depending on if you pass one in or not. And then I'm doing this simple, again, match query, so finding pictures, returning the URIs from the picture, and then getting the number of votes for that one picture by doing a order by. So I get the back in the right order from most votes to least votes. So I count how many of these incoming votes are, and return those two values, the URI and the number of votes. And then I save that into a map or as a list, and then I mark the transaction as success, and then return that data. So it's these two small functions that do the read and the write. Then I've got a controller for that. So for the eventual page that's doing a load without any bookmarking, it's doing a write again without any bookmarks. So it's just calling get the photos and votes, and then if you're doing a post request, it's just doing the votes and ignoring the results or ignoring the bookmark that comes back from that. If you're doing the consistent version of that, you're passing in whatever bookmark you've got. So this is a simple way in Spring to just do a routing. So you route the index to this method for GET requests. You take the bookmark as a query parameter and pass it along in that function that I wrote. And that then ensures that you do the transaction with that bookmark and you get the read that's consistent. The same thing with the write. So I'll do a post when I want to vote. That vote happens, I get back the bookmark, and then I do a redirect back to the index with that bookmark there, which then you will read again when you get back to here and the get. So that's how it works. If you're interested in how web pages, it's just really simple. That's annoying. A simple time leaf template that gets the photos, and there's a simple loop to put the image in and put the vote along with the button to vote for it again. So this is a super simple application, but it's a website that's interacting with a causal cluster, doing bookmarking, showing off consistency and user interaction and reading, writing. So it's fun, and the code for this is all online. So if you want to write your application with Neo4j, like web app like this, or on Spring with Heroku, this is a simple one that you can just start off with and get going. So, any questions? Because that's the end of the demo. Yeah.
What happens if you type in a number that's not available yet?
All right, that's a good.
Because that needs to be protected, right? That's the bookmark.
Right. So that's a good question. So if I go here and I do this, and I've got this when it loads, I've got the bookmark here as a query parameter, and it says 205 right now. What happens if I change this to something crazy?
Oh, just 206.
Yeah, so if I change that to 206, what happens? Well, there's no 206 transaction that happened yet, and if I would sit here, that's not going to happen. So it will just, in this web app I wrote that I didn't check anything like that, I don't have a timeout, so it will just hang forever. Neo4j will eventually will stop waiting as well, so it will not wait forever. But this is an example where you probably want to do something in your application to guard against this. But if you were just stupid and did that, then yeah, you're going to get stuck. So I can go, yeah, so it failed to read anything.
You can do the other half of the demo.
Yeah, so if I open up a new tab, if I just,
This is the coolest thing. This is the one that's exciting.
if I do that, and then switch back really fast, not fast enough, then it updated, because there is a transaction that happens. So yeah, if you put some, yeah, I could have opened another tab and click vote, and then, yeah. Yeah, okay, I can do that as well. So I can open that one, open this one here, open that one there, get them both open. Right, so if I vote here, or no, so if I go here and do 209. So that one won't work because 209 transaction hasn't happened yet. So I've got 209 here and 207 there. So if I go on this left side and vote, and then I think I have to do it one more time, they should both update. You should see, yeah. So causal clustering. Any other questions? Yeah. All right. I guess we're done.